if anyone is like new here, so no issues, because since we are starting a new chapter now, it will be good. No need of previous concepts. Okay, if you have missed a lot of classes, or if you haven't attended the classes, and the topics are missing, don't worry. This is a fresh start now with a very good, interesting chapter, that is wave optics. Okay, it's on your screen. You can also see on the YouTube. I've started the live streaming. Clear? Okay, it's working there. I'm audible, no, properly. Please reply in the chat box. If is there any issue, you can reply in the chat box. Otherwise, let us continue. Yes, wave optics. Okay. How are you, all of you students? How many students are there? Please reply in the chat box. Yeah, thank you for reply. Who is this? All is well, sir. Very good, very good. So we'll start the wave optics. It's very interesting chapter, okay? And okay, I have launched the poll for you. Okay, please reply in this poll. You're having few options on this. At certain, I'm audible. Reply yes or no. Click on the button. Okay, it will itself show you the colors there. And is the screen visible to you? Reply that also. As a screen visible, screen by screen, I mean the main thing is this: the PPT slides must be visible. If that's fine, then it's okay. Otherwise, click on no. I am taking on yes, yes, both. Yes, I am audible and the screen is visible. See, 5 students are there. Reply all of you. Only one have replied. Yes, JNV Faridakot student, JNV Mandi and JNV Shimla, all of you please reply. Okay, I'm ending this poll. Okay, let us start our chapter, that is wave optics. See, first we'll go through the contents of today's class. Okay, so what are the contents? Let us see this. What are the contents? Let us see this. So first we'll go through the Huygens theory. This is Huygens theory, okay? Then we'll go through the interference. Fine. Then we'll go through the diffraction. Then we'll go through the polarization. These are the contents of today's class. Okay. Okay, very good, JNV Mandi students. So write in your notebooks. It's a fresh starting, students. It's a very fresh chapter here. FRESH. Okay. Write the contents as like on the first page of your notebooks if you're making the notes. Otherwise, I am moving towards the next. Fine. Huygens theory. See, it's how we pronounce this word. Huygens. It's not Huygens. He was a Dutch physicist. Let me tell you something about him. He was actually a Dutch physicist. Okay. It's been pronounced as Huygens. Huygens. Then we'll study about the interference, diffraction, polarization. So are you ready, students, to go through this journey of new chapter? Okay. Our goal is what? To end the chapter, finish. The end is the goal. The end is the goal. Okay. So now let us move towards, okay, let us see some of the history points. History. So first we'll go through the history of this chapter, that is wave optics. We'll understand something about the history. This is our chapter, the wave optics. History. So it all started in the history in the year 1637 when a great physicist Descartes explained his own model of light. I mean, he explained like this: the light which we are able to see, explained this is made up of corpuscular model of light. I mean, he told light consists of particles of energy. Light consists of particles of energy. Okay. How many of you are replying on this? Light consists of particles of energy. And via this, he was able to explain only one of the thing, that is, he derived Snell's law. You know, we have studied in the ray optics or geometrical optics one thing, that is Snell's law is given by what? This formula, that is n1 sine I equals to n2 sine r. This what we already know. Okay. So Descartes just did one thing. He was able to explain this thing. I mean, he derived this formula. We are just using this formula as an application. We have seen this thing in the geometrical optics. But Descartes did a real work in this and actually have derived it. He did a derivation. Okay. And also he was successfully able to explain the process of reflection via his theory of corpuscular model of light, which says like this, that these are the particles of energy, blue blue ball, and when this falls on this surface, it gets reflected, observe, like by following what laws? You can say by the laws of classical mechanics. Okay, if we assume these are like particles of mass and something like this, corpuscles of particles, or corpuscles or particles of energy, we can say this: if it is falling on a wall at an angle I, at the same angle it will get reflected R. Okay, so through this he was able to successfully explain the laws of reflection. Okay, we'll not dive deep into this. It's like the simple incident ray and the normal and the reflected ray all lie in the same plane. Okay, and this is angle of incidence, this is angle of refraction. Okay, you can see here the angle of incidence is greater than the angle of refraction. The angle of incidence is greater than the angle of refraction here. Okay, so when the ray is coming like this, okay, it will bend towards the normal. Okay, so, and we have seen this thing, he was able to prove this. Okay, then this was in the 1637, remember it, this was when, this was in 1637. Then comes what? Then after the 1637, he has seen that comes a new scientist, that is in 1672. So after 1637, it is with a new scientist, that is 1672, Isaac Newton. He is known as what? The father of classical mechanics. He is the father of classical mechanics. Okay. He also modified the model of light, which was given by Descartes in 1637. Okay. He modified it and he was able to explain a lot of things, not only reflection and refractions. He explained something which is known as inflections, which we also haven't studied. Okay, and colors of light, this we have seen. Suppose there is something prism, okay, and white light falls here, so on the other side when it will go, it will show dispersion like this. This is dispersion, that is white light uh, got dispersed or got breaked into the 7 constituent colors, which is VIGYAN, that is violet, indigo, blue, green, yellow, orange, and red here. Okay, this is VIGYAN. So after this, in 1672, when Isaac Newton had given this model, so then comes what? Then after 1672 comes the year which is equals to 1678. So 1637 to 1672, and then 1672 to 1678. A lot of years of gap. Okay. After this came one more scientist. He's what? He's Dutch physicist. His Dutch physicist, Christian Huygens. This is what? Christian Huygens. Okay. And he has given the wave theory of light. Okay. According to his wave theory of light, he explained what? He given his wave theory of light, and he was able to explain properly, drive properly that how it is happening. That is reflection and refraction. Yeah, and all those things. Then after 1678, it was in the 1801, students. A very famous year. A very famous year when comes a young scientist named as Thomas Young. He was Dr. Thomas Young. Okay, he was a great physicist of his times. What it did, he also used the wave theories of light. Okay, and he was able to explain precisely, properly what interference process experiment. Okay, and he did also explain a diffraction also, many things. This ends the history. Okay, so up to 1801, the work of optics was carried on, and till today, it has been under research. Many things are being it's under research, so many things are being inverted, and few of the things are like being observed and explained, like rainbow and all these things. So in the optics, if we talk about the recent research, it's not under our scope. So we'll go towards the failures now. So failures of the Newton corpuscle theory, what is it? Because see, if you're accepting the newer theory, you have to reject the older one, and you must have the drawbacks for that. Okay. So Newton's theory was rejected, and in place of that, Thomas' theory was accepted. Another scientist theory was accepted. Okay. So Newton assumed actually that the light travels faster in the denser medium than in the rarer medium, which has been proved wrong, by the way. Okay. Fine. Because we have already seen in the geometrical optics that if this is a boundary separating two mediums, this is N1, this is N2, or this is refractive index N1, this is refractive index N2. See, this is a refractive index N1 means suppose it is a rarer medium refractive index. This is N2, suppose it is denser medium refractive index. Okay. And if the ray is passing like this is angle of incidence, and denser mein jayega, it will be denser like this R. So here you will know this thing that I will be greater than R here. Okay. Geometrical optics. In geometrical optics, if we switch back, we have seen this thing, students. The wavelength of the visible light was less than we did see. When we entered into geometrical optics, what happened actually, if you observe, it happened like this, we have assumed the wavelength of the light which we were using as equals to what? As less than the dimension of the objects with which it is interacting. Okay. So here it is what? Here these objects are what? These are convex. These are convex and concave. These are convex and concave mirrors. Okay. And some other like what? Lenses like this. These are biconvex lens. These are what? These are biconvex lenses. These are biconcave lenses. Okay. Fine. So when the light interacts with this, we have treated their dimensions. As very, very greater than the dimensions of the wavelength of the light which we are using for its interaction with this. Okay. So from this we can conclude like this: light can be assumed to approximately travel in straight lines. Okay. From geometrical optics law, we can consider like this: light can be assumed to be travel in straight line. That's why the ray optics is developed. No, you can see here, that's why the ray optics is developed. But if we see, yeah, if you see in this experiment, you can see properly that the straight line motion of the light is very much important here. Okay. So if you see here, the light is traveling like this. It goes into the eyes of this, you know, and he's able to observe it properly. But if you take a curved kind of this figure to see the light of the candle, see, ray can go like this, but it can't, if there are no mirrors on the edges, it can't get reflected like this and enter into the eyes. So this consider is not fulfilled here. This condition is not fulfilled here. Okay. So this is about geometrical optics. Now, wave optics is what? See, we have studied in geometrical optics. The conclusion is this: the light travels in the straight line. Clear? But now you'll feel shocked, students, कि wave optics taught like this. कि they don't like this thing. Okay, I mean, wave optics concludes like this: that the light doesn't travel in the straight line. It doesn't travel in the straight line. This will be concluded from the wave optics, and so a new theory will be developed. Now let us see first this thing. So you see here properly what is happening. See, it says like this: size of the obstacle in the path of the light is in order of the wavelength of light. Suppose the light is passing like this via some source. Let us take the first of all, let us take the plane rays. Suppose let us take the horizontal rays. Okay, and suppose on the path of it there is some object. So light rays will show bending, and this process is known as diffraction. So from this experiment, it can be seen properly that this shows that the light has been light has been deviated from its initial path. If something is deviated from the initial path, we say like this: it is no more in its straight line motion. So the conclusion which was made from the geometrical optics is now wrong, and now it's been concluded with the wave optics, that which will be your platform upon which we'll study all this chapter. Okay, so remember this, I'm marking this with a 5-star. 1 2 3 4 5. These are 5 stars given to this line. Remember this, it says what? Also one highlight, I'm highlighting it. So light does not travel in the straight line. Light does not travel in the straight line. This was concluded by wave optics. Take a note down in your notebooks. If you have noted it down, please reply in the chat box. Please reply in the chat box if you understood this thing and you have noted it down. See, now observe this picture. What is happening in this? Okay, what you're saying? Yes, sir. Okay, good. So see, light is coming like this. This is source of light, SOURCE, source of some light. And the light is coming like this via some wavefront patterns. Okay, very good, Mansa students. As it is all the points. Suppose this is a source of light, and okay, from where we'll consider the wavefronts. Okay, the light travels like this. And suppose this is some obstacle in the path of the light. Obstacle. So this picture is showing you deviation in the path of the light like this. This is a deviation in the path of the light. Gets deviation here. Okay. And this is what? Diffraction process. This is what kind of process? This is diffraction process, bending of light rays. Bending of light rays. Okay, finish. Now let us see the next. So from the wave optics, it was concluded what? That light does not, says what? Does not. Highlighted, does not travel in a straight line. Okay. So now let us see the theory, that is of Huygens theory. I mean, what he told in the Huygens theory, what are his principles? So now write these subtopics or subheadings in your notebook. Okay. That what is this Huygens principle? What are the wave fronts? So write all these things. I'm waiting for your reply. Write all these things, then we'll understand. First of all, starting with the wave fronts. So write fast because there is one very interesting and funny animation. Not funny, but interesting animation. Which is like waiting for you. Just write this subheadings. Then we'll start with that animation, wave fronts animation. Okay. So first we'll go through these wave fronts. That what is this wave front known as? Then we'll see Huygens principle. Okay. Then we'll understand reflection and refraction according to Huygens principle or theory. Then at last we'll see the Doppler effect. In the last, we will see Doppler effect. Are you ready, students? Got it? Last में क्या देखेंगे? At the last we'll see the Doppler effect. लिख लिया ये चैट बॉक्स में, रिप्लाई करो, जल्दी करो, रिप्लाई फास्ट. Now I will not wait. Again, you people are like wasting the time. Started with the story timeline, history, somewhat conclusions. Now we have arrived to the main theoretical physics theory part. Okay. Reply it. Reply, students. Okay, watch this animation. See, it's a very cool animation. Watch it. Okay. Watch this animation properly. So I have launched this. See what is happening on this. Let us see again. Okay. So what is happening? See, observe this thing. As the water has been dropped from a tap, drop by drop. So circular kind of wavefronts are being generated here. These are what? Circular kind of wavefronts. Okay. And if you see the side view, from this we can see the waves are being generated like this. The waves are being generated here like this. Okay. Yes. Also observe this. Suppose You set a vibration on the center like this, or if you throw a rock or a stone in a pond, throw a rock or a stone in a pond, or what, in a water tank. So vibrations are set up, and these, and if suppose you take a locus of the points, if you take a locus of all such points, students, which are in same phase matlab, if one is upper vibrated, other will be upper vibrated. If one is negative vibrated, other will be negative vibrated. If you take a such kind of case here, okay, such kind of case, if you take that one ka vibration up, other ka vibration up, all the particles will be having the same phase. If you connect all those points, the locus of all such particles which are having same phase is known as, here students, wavefronts. And these arrows are basically showing you that it is showing you the direction of the wave or the energy, where it is, in which direction it is traveling. Okay, I hope the animation is clear to you. This is known as wavefronts. Now let us see, after this wavefront, now let us see the definition of this. So the definition says like this: locus of the points which oscillate in same phase is called the wavefronts, and these are the wavefronts here. Okay. Suppose this vibration is set up at the center, so concentric circles will be created like this. Concentric circles are created like this. Okay, these are what wavefronts. See, light rays always travel in the perpendicular direction to the plane of the wavefront. This also remember. So if I show you, if someone is asking from you, okay, that's fine. If these are wavefronts, what is the direction of the wave traveling on this? So you will mark like this, that it is traveling like this. So this is the direction of which it's traveling. This is the direction of which it's traveling here, okay? See the speed. The speed with which the wavefront moves outward from the source is called the speed of the wave. Remember this part also. The speed with which the wavefront moves outward from the source is called the speed of the wave. Okay? Remember this. Suppose this is a center point and it's traveling like this. This is known as the speed of the wave. So now let us see the spherical wavefront. Now let us understand what is this thing known as spherical wavefront. See, you have already seen one thing, that is, if you throw a stone in a pond, circular kind of concentric vibrations or ripples are being set up. These are known as circular wavefronts. Similarly, if you keep a source of light in 3D, it will generate a spherical kind of wavefronts there. Okay. If a point source emits waves uniformly in all directions, and the locus of points which have the same amplitude and vibrate in the same phase are spheres. So these wavefronts are known as spherical wavefronts. See this video. This will show you, the arrows will show you the curved, I'm saying curved arrows will show you the direction of the wave. And these concentric spheres which are being made as this curves, lines increases, will show you the spherical wavefront. Reply in the chat box if it's clear. See, these are spherical concentric spheres of different shades of color you are able to observe. No, concentric spheres of different shades of color you are able to observe. These are the spherical wavefronts. Concentric spheres of different shades of colors you're able to observe. No, these are spherical wavefronts. So now let us see the plane wavefront. What is it? Very good. Now let us see the plane wavefront. So see, what is the plane wavefront here? Definition in the top. Note it down. In 3 minutes and 2 minutes, I'll ask you. I will proceed towards the next. Okay. So note it down. Okay, students. So have you written the definition? Please reply. Definition लिख लिया है? Okay, let us move next. Write Huygens principle. Write these things, okay? So what it says, Huygens says like this. I'll show you first, okay? Let us see first it, then we'll read the theory. Are you able to observe this? Okay. So Huygens says what? Huygens says that suppose you are having a source of light. Huygens says, suppose you're having a source of light S as shown on your screens. And suppose the light rays or the direction of the energy traveling of the electromagnetic wave, that is light. See, light is what? Also an electromagnetic wave. It's an electromagnetic wave. Okay. Suppose this is a source of light S and the wave direction is like this shown by the arrows. I repeat it. Suppose this is a source of light and the wave direction, I mean the energy wave direction, in which direction this light rays are traveling is shown by light wave is traveling is shown by this direction, these arrows, 3 arrows. Okay. So at any time t0, suppose I take the shape of the wavefront, because if this is a source, if these arrows are been showing the direction of the energy wave or the traveling wave, so it's sure that these arrows are perpendicular to some circular kind of structure, and that is a wavefront. So let us take such wavefront at time t equals to 0. So see here carefully. Okay. Up to here it's clear. A source of light, from its 3 arrows are showing the direction of the electromagnetic wave, which is a light which is basically traveling. And if these 3 arrows are showing the direction of the electromagnetic wave, which is basically traveling, it's sure that these arrows are perpendicular to this circular kind of structure at time 0. This is the wavefront initial. Okay, suppose this wave is traveling with v speed, है ना? So at any time t, it will cover, this wavefront will cover a distance vt. Remember this. Okay, let us take some few points on the locus of this point, this wavefront. On the surface, on the periphery of this circular looking wavefront, let us take some red points, which are basically few points here. Okay. So Huygens principle says like this: these points by themselves, by itself, these individual points will produce a second vibrations, okay, like this, and they will produce by themselves a secondary wavefronts, very small. So what Huygens principle says, there's a wavefront we know, but all the points which are in this wavefront will themselves act as a source of some other vibrations, which them by themselves will produce a secondary vibration, a secondary wavelets. Okay. Up to here, students, it's clear or not? Please reply in the chat box. This was the first point told by Huygens. He told like this: all the points on the wavefront will be acting as a source of secondary vibrations or secondary wavelets, or if I say simple language for understanding, secondary wavefronts. Please reply in the chat box if you understood this thing. Clear, hai na? Now what happened? Now suppose if I connect the periphery points of this secondary vibration wavefronts, I'll get what? I'll get a new wavefront which is shown by dark black color. So this can be concluded like this: if the waves is having the speed of v, so in a time t, it will cover a distance v tau or vt, and a new wavefront direction you will get. So it is can also be explained. I mean, expansion of the wavefront or traveling of the distance of the wavefront from t0 to t equals to tau, which is equals to vt, can also be shown by the representation of this diagram, that is of what? Joining the secondary vibration peripheries. Okay. So this is new wavefront. I mean, that wavefront, suppose it was here, so it is a new one. It has traveled this much distance, that is v into t, x in time t. V was the speed of the wave, and this in turn, and suppose say this was for a source of light, maybe 2D, maybe 3D, but this is a planar wavefront. So for planar wavefront, all the point on this planar wavefront will be acting as a source of some second vibration, When we join the periphery points, we'll get a straight line there. And remember, backward is rejected. Backward for this is also rejected. Never join the back points. Backward is, if anybody is having the doubts, okay, sir, can we join the back points? Never join the back points. Back points are rejected. And here also the back points are rejected. Okay. Back points for both of them are rejected here. Fine. Now, see students. This. Now, if you have understood that concept, write the theory. Then we'll end the class. I'll ask the doubts, then we'll end the class. Write this theory, students. Because practical slide you have already seen. So now write the theory. Written students, write the first point. This was according to Huygens principle. First point, then the second point. Okay, students. So now let us see somewhat about the refraction and reflection explained by the Huygens principle. Okay. So let us consider the refraction of light by Huygens principle. Okay, so are you ready? Please reply in the chat box. What do students are doing? Sleeping? Reply in the chat box. No. Genuine Shimla students, everything is fine. समझ में आ रहा है? Or you need to go back. You need me to go to back slides. What do you say? JNV Farid quote. JNV Mandi, JNV Mansa. Please reply in the chat box, students. Farid quote students, yeah, you people don't reply. What happened? You are new, fresh students. You must reply. The chapter is fresh. Okay. So are you ready for this refraction of light waves by Huygens principle? Let us see somewhat, okay? Then we'll end it, no issues. No doubt, very good. See, इसमें क्या होता है? Suppose okay, you're asking, see, ऐसा नहीं होता है. You're saying backward. Backward, it doesn't make sense. See, it is with respect to reference point, JNV Shimla students. It is with respect to reference point. Suppose I throw a stone here in the pond of water. Ripples are generated like this concentric vibrations. Remember one thing. If I am saying this is forward, what you will say? This is backward? No. It's with respect to your reference point. If you're taking this as reference point, you will say this is forward only. If you're taking this as reference point, in this side you're facing, you'll say this is forward. If you're saying here, this is forward. If you're saying this is forward. So it depends upon your frame of reference where you are. Don't consider like this. It's not like this. It's moving backward. Moving backward is not. It's always moving forward only. If you turn here, east, it's here. South, it's here. West, it's forward. North, it's forward. Got it? I hope it's clear. जिनमें शिमला students, it's clear. Backward का तो कोई sense नहीं ना. That's why they are not taking. There is no sense of backward students. Okay, that's why they are not taking there. Backward ka there is no sense. Now let us understand this. There is refraction of light waves by Huygens principle. Suppose there is some, this is some tub having some liquid, whatever, okay, and This is denser, by the way. Okay. And this is having a refractive index N2 here. And this is some medium air which is having refractive index N1 here. Okay. Suppose the waves, the light rays are coming like this, like this. Okay, they will pass on when they will strike on the surface, the boundary separating two mediums, they will deviate like this. Okay, this is the angle of incidence. This is the angle of R. Okay, where we'll say angle of I is greater than angle of R. Okay, so what it did by using all these things, he was able to derive this formula. I remember this formula. It's important, students here. Okay, यहाँ पे this formula is important. Okay, this is very important. So I can show you this, that suppose if this is angle of incidence and if this is angle of refraction, the speed of light in this medium which is having a refractive index N1 is V1, and speed of light in this medium which is having a refractive index N2 is V2. Okay, so we use this formula, remember it. So we use this formula, students. I've highlighted it. Okay, ठीक है. So see, after this, remember this application. Isme see, all of the things will be provided to you in the PDF. Okay. Isme, if anybody is interested in the derivation, he or she can see, but no need to go back towards in that direction only. Okay. Remember the main thing, the application part. So from this, I can conclude like this. I know already from the Snell's law. Snell will say, I already know this thing, that N1 sin I is equals to N2 sin R. Okay. So sin I upon sin R equals to N2 upon N1. Okay. Which by themselves it will give you N2 upon N1 here. So this is actually equals to this. Remember this formula, it's very important. Okay. And this will be equals to lambda 1 upon lambda. Remember it. Simple. Now let us understand the reflection process. Okay, reflection process kya hota hai, students? Okay. So if you focus on the reflection, suppose this XY is some reflecting surface, and the light as a wave, number of rays is coming like this, and it will show the reflection by following the laws of reflection. We already know. What are the laws of reflection? Incident ray normal to the incidence, and reflected ray all lies in the same plane. Angle of incidence is equals to the angle of reflection. Okay. So this Huygens principle, by using the Huygens principle, we are also able to derive this. That is laws of reflection. We are able to prove this via Huygens principle. No need of derivation and lot now here. Okay. See, if you want to understand that, I'm explaining you. See it carefully. For you people, I'm explaining you again. So suppose the rays are falling on a reflecting surface XY like this. If I connect this will be the lateral, this is the parallel difference between the rays, this ray and this ray, the perpendicular between that. Okay. Suppose the wavefront has reached here. So direction perpendicular to the wavefront will give you the direction of the energy wave traveling. Now you can do like this. No, it's maybe the wavefronts will be like this. Here, perpendicular to this. Why? This shows the direction of the wave. and this is the wavefront direction. And if you join this both via some geometrical laws, you're easily able to prove this thing, that BC, which is basically this, equals to V tau, AE is equals to BC. So these are some, I mean, these are the sides of the triangle. If I take this side, that is this triangle, if I take, okay, then I take this triangle. So I can prove angle I equals to angle R from this by congruency. Angle I is equals to angle R. This is among one of the laws of the reflection, okay? See, now it says, you can see on your screens, laws of reflection and refraction is same as in the optics. So all of the things which you studied are same, but the Huygens principle basically gives you the proof. In the geometrical optics, students, you haven't seen the proof. We haven't seen the proof. Reflection, angle of incidence, angle of normal to the plane of incidence, and reflected ray all lie in the same plane, first law, and angle of incidence is equals to the angle of reflection. These two proofs we haven't seen in the previous class. Also, when we were studying the refraction process, we didn't study how we are able to derive the Snell's law, n1 sin I equals to n2 sin R. So the things are same, but Huygens principles give you the thorough derivation of that. Okay. So here it is, behavior of wavefronts after reflection, refraction. This is the last topic. After this, I will end the class. Suppose you pass the rays on a concave mirror. Of course, it will come at a particular point, maybe focus this is. If you draw perpendicular to it, this will be the direction of the wavefront shown. We say AB is incident wavefront, CD is the reflected wavefront. Okay, convex case mein, it will appear to, image will be appearing to like it's been made at the back, virtual image. So for this, if AB is incident wavefront, okay, CD will be the reflected wavefront, and virtual wavefronts will be drawn like this. So this is the picture. So suppose this is a, now let us talk about the lenses. Suppose this is a lens, biconvex lens. Rays are going like this, it will converge at a point. This is the structure of wavefront now. Okay, and suppose this is concave lens. If this is a wavefront here, so we'll say when it will go, it will appear to come from a particular point. So this will be the new direction of the wavefront. So here it is incident wavefront, here it is refracted wavefront. Here it is incident wavefront, here it is refracted wavefront. Okay, now let us see. Time is up. Okay, students, the time is up. In the next class, we'll start with the prism proof. Okay, is it fine? Thank you so much for your attendance, students. All of you, very good. You are doing so good. Yeah, okay. JNV Shimla, JNV Mandi, JNV Freethcourt students, very good. Now I'm launching a poll for you. Please participate in that, so I can, you know, I mean, we can have more interactions after that, if you want. Also, I'm providing you my number. Maybe I provided so many times, I don't know, we forget. This is the personal number. If anybody is having any doubt, can ask. Okay. If you are facing any doubt, you can ask. You can reply on the chat box now also, or you can reply on the WhatsApp. We can make a separate group for doubts. WhatsApp group for the doubts. Individually, less students, only quality students. Okay. GNV quality students. Reply in the chat box and then you can leave. Bye bye everyone. Take care. Study well. If you're having any doubt, you can ask in the class only now. I'm here for at least up to 5. Bye GNV Shimla students. Bye everyone. Bye everyone. Okay. Okay students, bye all the YouTube students. I'm going to end the class now.